Welcome to this explainer. I am absolutely thrilled you're tuning in today because we are going to look at one of the most fascinating, complex structures in the human body. You know, when we think about the liver, it's so easy to just picture it as another organ sitting quietly in the abdomen doing its thing. But today, I want us to reframe that entirely. The liver is the body's ultimate metabolic engine. It is a tireless multitasker working around the clock to keep your entire system in perfect balance. But what actually happens when that engine starts to sputter?
Picture this for a second. A patient comes into the clinic. Their skin has taken on this distinct yellow hue, they're experiencing sudden, severe confusion, and they're just profoundly fatigued. It sounds like a total mystery, right? You've got skin issues, brain fog, and massive energy depletion. But these seemingly disconnected symptoms actually point straight back to a single source, the liver. When this ultimate multitasker fails, it doesn't just quietly shut down in the background. No, it sets off a series of massive systemic alarms across the entire body.
So, here is our roadmap for today. First, we'll cover the liver's crucial roles. Second, we'll look at the waste crisis involving bilirubin. Third, the energy crisis of hypoglycemia. And finally, brain under pressure.
All right, let's jump right into Section 1, the liver's crucial roles as the ultimate metabolic engine. Before we can really understand the pathology, we have to understand the machinery of a healthy liver. Think of it as having three primary identities. First up, it's a massive chemical processing plant, totally responsible for breaking down and clearing out metabolic waste, like bilirubin. Second, it acts as the body's battery, an energy reservoir, precisely managing our glucose levels so we have fuel whether we just ate a huge meal or we're fasting. And third, it serves as a critical neurological filtration system, constantly pulling toxic byproducts like ammonia out of the blood before they can ever reach the brain. When liver failure strikes, it is exactly these three pillars that collapse, causing this huge domino effect of disease.
That brings us to Section 2, the waste crisis, bilirubin. Basically, what happens when the processing plant shuts down.
To really grasp this waste crisis, you gotta know where the waste actually comes from in the first place. Get this. A staggering 70% of bilirubin is derived directly from the catabolism or breakdown of hemoglobin released from senescent, meaning old, red blood cells. Your body is constantly recycling these red blood cells, which means your liver is under a constant, heavy demand to process this specific byproduct.
Now here is the incredible chemical transformation the liver performs to handle this. When bilirubin is first produced, it is what we call unconjugated. This means it's hydrophobic. It literally hates water. Because our blood is mostly water, this unconjugated bilirubin has to hitch a ride on a protein called albumin just to travel to the liver. But once it arrives, the liver uses a magical enzyme called UGT1A1. This enzyme converts the hydrophobic waste into conjugated bilirubin, making it hydrophilic or water-loving. Once it's water-loving, the body can easily excrete it right into the bile without needing any transport proteins at all. It's an absolute masterstroke of biochemistry.
But what happens when the genetic code for this whole pipeline is broken? Well, depending on the micro-level defect, we see wildly different outcomes. Take Gilbert syndrome, for example. The UGT1A1 enzyme activity is just slightly reduced to about 30%. It's usually totally benign, with bilirubin staying under 3 milligrams per deciliter and often only spiking during periods of stress or fasting. But if you look at Crigler-Najjar syndrome, the enzyme is drastically reduced or even completely absent. This is a severe medical emergency, with bilirubin skyrocketing anywhere between 20 and 45. And then there's Dubin-Johnson syndrome. This is a rare mutation in the MRP2 transporter. Interestingly, the liver function tests actually look normal here, but the impaired excretion causes this fascinating dark pigmentation, literally resulting in a black liver. So how do these micro-level enzyme and transporter failures actually present in a patient standing in front of you? Well, when bilirubin accumulates past that 3 milligrams per deciliter mark, the patient presents with hyperbilirubinemia. The most obvious sign is jaundice, that unmistakable yellowing of the skin and the sclera, which are the whites of the eyes. But remember, the waste has to go somewhere. Because the gut is being starved of bilirubin, the patient will have very pale, acolic stools. And because the kidneys are working in overdrive, trying to help clear the water-soluble conjugated bilirubin, the patient's urine will turn notably dark. The processing plant is failing, and the evidence is entirely systemic.
Okay, moving on to Section 3, the energy crisis. What happens when the battery drains?
Let's look at what goes wrong when the body's primary battery runs dry. In a healthy state, the liver is the ultimate guardian of glucose homeostasis. When you eat a big meal, the liver performs glycogenesis, packing that excess glucose away for a rainy day.
When you're fasting or sleeping, it triggers glycoanalysis, breaking those stores back down to keep your blood sugar perfectly stable. And if those stores completely run out, it literally makes new glucose from scratch through a process called gluconeogenesis.
However, chronic liver disease, like cirrhosis, acts as a devastating double-edged sword on this delicate system. First, the physical fibrotic scarring of the liver wipes out its ability to store glycogen. The size of the battery physically shrinks. But simultaneously, the failing liver stops clearing insulin from the blood. This traps the whole body in a state of chronic hyperinsulinemia, basically insulin dominance. The high insulin tells the body to stop producing glucose, while inflammatory markers like TNF-alpha further disrupt normal signaling. So you have no stored energy, and your own hormones are actively preventing you from making more. It's a complete catch-22.
So the crucial point we really need to establish is when this becomes a full-blown medical emergency. While diabetic hypoglycemia is typically diagnosed when blood sugar drops below 70 milligrams per deciliter, non-diabetic patients with acute liver failure can exhibit pathological hypoglycemia with blood glucose plunging below 50 milligrams per deciliter. That is a profound, incredibly dangerous lack of energy for the body's most vital organs.
When blood sugar tanks like that, the body screams for help in two distinct ways. First are the autonomic symptoms, which are driven by adrenaline. Think palpitations, excessive sweating, and anxiety. Second are the neuroglycopenic symptoms, and this happens when the brain is literally starving for fuel. This leads to dizziness, extreme confusion, and eventually coma. But here is the truly terrifying part for liver patients. Concurrent hepatic encephalopathy, which is brain dysfunction caused by liver toxins, can completely mask these neuroglycopenic signs of low blood sugar. The patient might just look like their liver disease is naturally progressing, when in reality, they are rapidly running out of glucose and crashing.
Managing this specific energy crisis requires some really strict dietary interventions. Current guidelines actually recommend a Mediterranean diet with a surprisingly heavy emphasis on carbohydrates, about 50 to 65% of total intake. And because the liver can't store large amounts of energy anymore, patients have to eat small, frequent meals to keep a constant trickle of fuel in the system. Continuous glucose monitoring, or CGM, is a total game changer here too. Though, we really have to acknowledge the real-world challenges. Patients with advanced liver disease often suffer from severe anorexia and early satiety, making it incredibly hard to consume these necessary calories, not to mention the heavy financial cost of maintaining specialized diets.
Which brings us to our final pillar, Section 4, Brain Under Pressure, the Filtration Failure.
Let's see how this all builds into an acute, life-threatening neurological event. When the liver stops clearing toxins, specifically ammonia, the brain takes a direct and devastating hit. And it's a very specific part of the brain that suffers. Astrocytes are these amazing, star-shaped glial cells that support our neurons. While astrocyte swelling is the single most consistent neuropathological finding in humans with acute liver failure. The ammonia reaches the brain and triggers cytotoxic cerebral edema. This means the brain cells themselves swell up with water, dangerously increasing pressure inside the skull.
The actual mechanism behind this swelling is fascinating. Researchers call it the Trojan horse hypothesis. Let's walk through this molecular betrayal step by step, because it's wild. Step 1. Because the liver isn't filtering it, excess ammonia freely crosses from the blood right into the brain. Step 2. The ammonia enters those star-shaped astrocytes, where it gets converted into an amino acid called glutamine. Step 3. This is the Trojan horse moment. The glutamine acts as a cellular smuggler, carrying the ammonia deep into the astrocyte's mitochondria. And finally, step 4. Once inside the mitochondria, the glutamine breaks down, unleashing massive amounts of ammonia locally. This triggers explosive oxidative stress, complete energy failure, and forces the astrocyte to swell massively with water. Now you might be wondering, does the blood-brain barrier just completely blow apart during all this? Surprisingly, human studies show it doesn't completely break down at all. Instead, as this quote perfectly highlights, there are just these subtle, microscopic alterations in the protein composition of the tight junctions between the cells. The gates don't get blown off their hinges, they just get slightly misaligned. But that tiny slight misalignment is literally all it takes to allow a devastating flood of ammonia and water into the delicate brain tissue.
And that brings us to the very frontier of current medical research. We've seen today how liver failure is never just one isolated problem. It is a systemic collapse of three massive pillars. You have the waste crisis of bilirubin, the severe energy drain of hypoglycemia, and the incredibly dangerous neurological pressure of cerebral edema. The liver, truly, undoubtedly, is the metabolic engine of human health.
But with exact molecular mechanisms like the Trojan horse still being unraveled by science, we have to ask ourselves, how close are we to developing targeted therapies that can protect the brain and stabilize glucose before the liver's engine completely stalls out for good? It's a profound question, and one that researchers are working tirelessly to answer. Thank you so much for joining me for this explainer, and remember to keep questioning how our incredible biology works.